Today we're going to discuss valid and invalid arguments. Now, in mathematics, argument isn't when two people are fighting each other. Rather, it's a sequence of statements that are called premises ending in a conclusion. So think about trying to prove something to another person. You're going to present them with the logical sequence of events and draw a conclusion based on the evidence provided. Now, these statements that you're putting together that are called premises are actually going to be the different statements. So you're going to say that the evidence for something, let's say statement P1 and something else, P2, and however many of these supporting statements you have, these are what we call premises, ending in a conclusion. So the premises will imply some kind of a conclusion. Let's call it Q. This is one form of writing it, and these contain all of the operations that we've already seen applied within logic. The other way to represent such an argument is going to be in a tabular form. So we're going to list all of the premises vertically. Then we're going to draw a horizontal line, have 3 dots that we read as therefore, and list our conclusion. So once again, these are what we call premises, supporting evidence that we assume to be true, and this is what we call a conclusion of an argument. Now, just because you've laid out an argument doesn't mean that it is necessarily correct. So we need to define what it means to be valid. An argument is called valid if the premises logically imply the conclusion. So this sequence actually is proper. The conclusion is true when all the premises are in fact true. So that is the assumption that we're going to make. Whatever you list as premises for the evidence, we're going to assume are true. And if the conclusion follows from that and is also true, that means that the argument is valid. If you are presented with an argument, there are ways to test its validity. First of all, we need to figure out what are the premises and what is the conclusion, so we can talk about those parts separately. We can construct a truth table to show that the premises are all true when the conclusion is true. And then we need to deal with the case when that might not in fact happen. So for that, we need a definition. A row in a truth table where all the premises are true is called a critical row. Notice that an argument is valid when the conclusion is true for all premises being true. So this part is what is called a critical row. If the conclusion is also true in this row, that means that the argument is valid, as per the definition. If the conclusion is false in that row, then we've just found ourselves a problem, and therefore the argument is invalid. In this case, we also say that we have found a counterexample. So this is what we're going to call this particular situation. Now let's take a look at how that works in the actual example. As I already said, arguments are usually presented in this tabular form because it's a little bit easier to read vertically all of the premises rather than if they are connected by a long series of conjunctions. So here we have the premises are P implies Q and P, and the conclusion is Q. If you wanted to write it out in this longhand form, we will list every single premise and then connected with an and. So we have P implies Q is our first premise, and our second premise here is just P. And then we will translate this horizontal bar and the therefore as an implication, and finally list our conclusion Q. Okay, so once again, these are my premises, and this is my conclusion in this particular form, whereas if you write it out longhand, your premises are going to be the first part of the implication, and the conclusion will be the second. Also notice that you have to be careful. You might actually have more than one implication within. All the premises will be connected with an and the main implication will follow between premises and the conclusion. Similar, for example, we have here, and you can notice light differences. So my premises here are P implies Q and Q, and the conclusion that we're trying to draw is P. Next, let's figure out, are these presented arguments valid or not by following the above stated procedure for testing the argument validity. So let's start with this one. We've identified the premises and the conclusion. I have two premises, one conclusion. Normally you only have one conclusion. We're going to construct the truth table for this entire expression. So I'm going to have my P, I'm going to have my Q, I'm going to list all of my premises. So in this case, it's P implies Q and P. And I'm also going to include the conclusion again. Now I know that I'm repeating many of the columns here, right? So I start with P and Q because these are my two defining variables. And then I also repeat them here because one of them also happens to be the premise and one happens to be the conclusion. This is only repetitive because this example is fairly small, but it's just generally good practice to do it so that you don't lose information about what exactly is a premise and what exactly is a conclusion here. Okay, so let me also identify them here. The reason that these columns are present is because these are my premises, and the reason that this column is repeated is because that is my conclusion. Now I fill in the table the exact same way we have filled out the truth tables before. I will simply go through all of the possibilities for P and Q, and I will fill in the corresponding columns with their respectful truth values. So the implication is only false when true implies false, which means this will be false here, and it's going to be true everywhere else. Now again, normally I would have to do a little bit more work for the rest of the premises and conclusions, but in this case I will simply repeat my columns. So the P column is true, true, false, false, and the Q column is true, false, true, false. Now, remember, we need to identify critical rows. So the critical rows here. The critical row is the row of a truth table where all the premises are true. Nothing so far about a conclusion. So I have to look at my premises, I have to look at all the columns that correspond to my premises and find the rows that are all true. So out of these rows where both of the premises are true, I see that I only have one such case. This first row here. That's when both of the premises are true. At least one of the premises is false in all the other rows. That means that I only have this as my critical row. And then I need to check what happens to that row, or to the conclusion in that row. I only have one critical row, so it's easy enough to check. I have to look at the conclusion. If the conclusion is true, then the argument is valid. If the conclusion is false, then we've produced a counterexample. Here, the conclusion is true, which means that this argument is valid. So I can write that down here. Okay, so again, remember that the justification for why the argument is valid is that in every critical row, which is the row where all the premises are true, the conclusion is also true. Now let's see what we can say about this argument, if it's going to be the same actual validity. So we're going to go through the exact same process, but now with different premises and a different conclusion. So I'm going to once again have my starting variables P and Q. I will then include columns for the premises, which are P implies Q and Q. And then I will include a column for my conclusion, which in this case is P. So notice a very subtle difference between the last example and this one, right? I've simply swapped one premise and one conclusion, but it's very quantifiably different. Premises are my assumptions. A conclusion is my final conclusion. So in this table here, again, you don't have to do it once you have had a lot of practice, but I'm going to label my columns here to keep track of what I have to identify in terms of the critical row. And then I fill out the table. Again, similar as before, I'm going to list all the possibilities for true and false in terms of P and Q. And then I'm going to fill out the rest of my table as per those operations that are listed. So P implies Q, I have true, false, true, true. And now I have to repeat the column for Q, which is my premise. So true, false, true, false. And then a column for P. True, true, false, false. Next up, I have to identify all the critical rows. So the rows where both of the premises are true. Can you spot which row or rows are those? Well, in the last case, I only had one critical row, but in this case, I actually have two of them. The premises are both true in this row, and they're also both true in this row. So I have myself here two critical rows, this one and this one. These are my critical rows. Next up, I have to look at what happens to the conclusion in these rows. If the conclusion is true in every critical row, then the argument is valid. If it is false in any one of them, then it is invalid. So I look at the conclusion in the critical rows. Are they always true? Well, no, clearly there's a false here. The moment you have at least one false, that means that the argument is immediately invalid. So because of this false in this critical row right here, I know that the argument is invalid. Now, furthermore, I can actually give sort of evidence to why that's invalid in the shape of what we called the counterexample. Let me just move this up a little bit out of the way. So the counterexample are the actual values for P and Q in the critical row that indicated the invalidity of the argument. So remember that the problem was in this row right here, where both of the premises were true, but the conclusion was false. The P and Q values that correspond to this row will appear right in the beginning of the table. So I can list as my counterexample here the value for P and Q that produced the critical row that indicated that the argument is invalid. So I extend my row throughout the entire table, and I look at the value for P, which is false, and the value for Q, which is true, that produced the truth value for both premises and the false for the conclusion. This is now my counterexample. Now, if we have to do everything with truth tables, we've already decided that truth tables are onerous and labor intensive. So last time when we were talking about logical equivalences, what we came up with are ways to prove certain laws like commutativity law, associativity law, and a whole bunch of others, De Morgan's laws and whatnot, so that we can create shortcuts for knowing when something is the same without having to construct a truth table over and over and over again. Something similar is going to be true within the valid arguments. We're going to call these rules of inference. These are forms of arguments that are valid. So once we have proven that an argument is valid, we actually have ourselves a general structure that we know will produce a valid argument. Because the truth table only says for all the premises that are true, the conclusion being true implies the validity of the argument, which means that the general structure of the argument is that of a valid one. There are a number of different rules of inference that we're going to see on the next page, but for example, this is one of them. This one is called modus ponens. These are Greek terms, sort of traditionally named, let's say, and this is exactly the form that we have just shown to be true here. This argument is valid, and so we can write it down as a form that we can refer to later. Now, the key thing to remember here is, again, similar to the logical equivalence statements, is we're really after the structure here. So you have to sometimes squint, as I call it, and see the real structure within the argument, not exactly the labels that have been given in this particular case. For valid arguments of this structure, the P and Q statements can be replaced by more complex ones. It's the underlying structure that matters. So if you can see through the actual structure, you will have yourself a valid argument. So for example, this is the simplest form in which I can write the modus ponens. But if I have an argument like this, for example, I have P and Q implies R, P and Q, therefore R. This argument is also in the modus ponens form. Because look, you have to think about what is the underlying sustenance, let's say, of the actual argument. You have thing 1 implies thing 2, thing 1, therefore thing 2. Well, that's the same as here. Thing 1 just happens to be more complex, but it's still just thing 1 implies thing 2, thing 1, therefore thing 2. The exact same structure, although they look different, but it means that if this is one of my rules of inference that has been proven to be a valid argument form, then so is this. Here are some common rules of inference that we will rely on throughout. So again, remember that in order to actually prove that these are valid argument forms, someone at some point had to go through the actual truth table and finding critical rows. So it's still an important method. But now that we have these argument forms, we can use them directly. Let's just go through and see what the structures of them are. First of all, we have modus ponens, as we saw on the previous page. P implies Q, P, therefore Q. From Latin, this actually translates to method of affirming. So you have an implication and then you affirm its premise and you therefore reach its own conclusion. Next one is modus tollens, which from Latin is method of denying. And here we have the denial structure in the second premise. So P implies Q, not Q, therefore not P. If you were to write it out, you would notice that this has the feel of the contrapositive, right? You are denying the conclusion of the original, and overall, you then conclude the denial of the original premise. Conjunction simply allows you to glue things together. P, Q as premises results in P and Q as a conclusion. Now remember from the previous page, the way to glue the premises together is to actually have and joining them. So this is essentially what the conjunction is allowing you to do. Generalization allows you to attach a previously non-existent premise to any premise via the operation of disjunction. If you start with just P, you can always attach or anything to it as long as you keep the original P. Specialization strips the additional information down. If you have a statement that is P and Q, then we certainly have just the P. Or, similarly, we could also have the conclusion here being just the Q. Again, remember, it's the underlying structure that matters, not the exact labels on the actual statements. Proof by cases might be a little overwhelming at the beginning. This is the first, 3-line one. But what we start with is P or Q, and then we have that P implies R and Q implies R. So no matter what, R is implied by the fact that we have either P or Q, and either one of them will result in R as a conclusion. Elimination allows you to get rid of one of the variables. You start with P or Q, and then you're very specifically told that it is not the case that Q. Therefore, we must have P. Transitivity is kind of like a chain reaction. If P implies Q and Q implies R, it means that we can skip the Q as the middleman and draw the conclusion that P implies R directly. The contradiction, remember that C stands for a statement that is always false. We have that if not P implies contradiction or false, it means that we must have P instead of not P. Now, you don't have to memorize any of them, and please don't. As you use them throughout, you might simply remember some, but have this as also yet another table that you print and keep by your side as you're going through these various exercises on applications of the rules of inference. So let's see how this will work out. We're gonna exercise with two different arguments here. Now, remember again that we have our premises and we have our conclusion. we could draw ourselves a truth table, and then we could look for critical rows and figure out if the conclusion is always true in the critical rows or is sometimes false, and then that way decide whether the argument is valid or not. In this case, though, we're going to use rules of inference as the way to directly apply the already proven laws. Now, it might be easier to actually have all the information in one place. So what I'm going to do is I'm going to rewrite all of the premises and label them so I can refer to them a little bit more directly. So here are all of my premises. And as before, every time I write something down, much like in the logical equivalences, I'm going to justify where this comes from. So each one of these is simply a premise. So my reason for including it is that, well, those are the things that I was given. Now, once I have the three of them, I have to include other equivalent steps until hopefully at some point in time, let's say on the 10th step or on the 50th, I don't know, I draw my eventual conclusion. If I'm able to draw R as a conclusion, that means that the argument is valid. So using all of these rules of inference above and these as my premises, what can I apply? I notice that I have P implies Q and I have P, which is exactly the shape of the modus ponens. And I have both of these as my premises here, which means that in my next line, I can include the conclusion for the modus ponens argument form, which is Q. So I will conclude Q here, and I will include the justification for where I got it from. This is from 1 and 2 and modus ponens. Okay, so I have now these as potential things to use alongside with my laws. Remember, you should keep your conclusion in sight because this is the one you eventually hope to reach. So I am trying to reach a conclusion that has R in it, and so far the only premise or the only anything listed that I can use that has R is this third line over here. Can I somehow use that to reach the conclusion? Well, I noticed that actually between the 3 and 4 of having not Q or R and then Q is actually of the same form as elimination. I have a premise that is connected, there are two statements connected with an or, and then I have a negation of one of them, which makes me conclude that it's the one not negated that must be a conclusion. So here, it's the exact same thing, but I've also applied negation in a different way, right? So I start with, let's say, this is my thing 1 or thing 2, and then I have a negation of the thing 1. Okay? This is what I mean about you have to really look for structure and not the exact same symbols. Here, I had sort of like, let me call this thing 1, and then I had not thing 1, which led me to conclude the other one. It's the same thing here. I have this as my thing 1, and this as my not thing 1. And therefore, I can conclude that the other one must be true. So my conclusion here is R, and my justification for it is I took lines 3 and 4 and applied elimination. And we're done. So this was a fairly short one. Again, as long as you can abstract the structure a little bit and spot how you can use elimination with the not added to both the cues here. This will take some practice, first of all. And second of all, I should point out that it's not that this is the only way to proceed. You might have been able to apply some other rules to rules of inference to these premises to begin with, or to any set of premises that you actually derive in order to reach the same conclusion. There is always more ways than one. Let's see how this one works out. So again, I start by rewriting all of the premises because I would like to be able to refer to them by name. And this one already looks a little bit more complicated because there seems to be more nots all over the place. So my justification for all of these is the fact that they're all premises. So how can I put any of them together in order to eventually reach R as a conclusion. Keeping in mind that you're targeting R will help, maybe not in the first couple of steps, but eventually, because if you have, let's say, a whole bunch of premises that deal with only P and Q, you're never going to reach R as the conclusion. So you have to start involving statements that have R in them so that that can actually appear as a part of your argument. Again, there's more than one way to proceed, so the law that I can spot first isn't necessarily the law that you will spot first for the application. So I encourage you to pause the video and try to see if you can apply any of the rules of inference to these premises, and then hopefully work your way towards the conclusion in some fashion. Now, the one law that I can see applies is actually this transitivity law. I have two implications, and that's the law that has two implications. So what I have is not R implies P, P implies not Q. So I can skip this middleman of P and have the conclusion of not R implies not Q directly. So not R implies not Q. And again, I include my justification. It's 1, 2, and transitivity. Great. What else can I do here? Well, I have the not Q and Q here, so I hope that I can somehow put two of these together. So I start with thing 1 implies thing 2, and then Q here is actually the negation of my Q there. So can you spot how I can actually use the modus tollens here? Another way to proceed is to actually start with something like just the straight up number 4 and apply one of the previous rules that we know something about. So if you have yourself a implication, what are the equivalent forms to the implication itself? Remember that contrapositive is logically equivalent to the implication. Now, I know it's not listed as one of the tables, but that is the rule that we've already proven to be true, so we can use that as well. So let me use that because it doesn't appear as rules of inference above, but I want to make sure that you know that everything that we know is valid up until this point is still valid right now. So the contrapositive says we're going to flip the order and negate both sides. So the contrapositive of not R implies not Q will be Q implies R. Okay, and this is taken straight from number 4 as a contrapositive. Okay, now I have this. Q implies R. I'm trying to draw R as a conclusion here, so I can see that I can put together Q implies R and Q and apply the modus ponens directly. And in fact, this will give me the same conclusion as if I applied modus tonens actually at step 5. So that would have been a little bit faster, but we're not about faster here, we're about exploring potential alternate directions. So I will conclude R, and my justification is from 3 and 5 and modus ponens. I know it can be overwhelming to look for these patterns because you won't have just the one way of doing it. And so you might sort of go a little bit around in circles here and there for a while until you actually spot your own conclusion. But with practice, you will get better at finding the rules of inference that are better applicable for certain cases than others. So please go through a bunch of these examples to get used to actually applying all of these different laws in the different substructures. Notice that the one particular problem with the approach of using rules of inference is the fact that if you have not reached the desired conclusion, you might not be sure if you haven't reached it because you just haven't persevered far enough, or because it cannot be reached due to the fact that the argument is invalid. Now, if you've managed to reach a conclusion that's directly opposite of the one listed, so for example, if somehow I've concluded negative or not R here, then I would know for certain that the original argument is not valid because I managed to conclude something that's exact negation of my alleged conclusion. However, otherwise, it's still pretty unclear. In that case, you can always go back to the truth table technique and use that to prove the validity of the argument. I'm going to leave these two exercises for you for extra practice. Notice that your truth tables here are going to be quite extensive. You're going to need 3 variables here and 4 variables here. Look for critical rows where all of the premises are true and see if the conclusion in that row is also true. If it is, the argument is valid. If it's not, then it is invalid. But let's take a look at other examples of the, first of all, word forms that we will have to turn into symbolic form and then think about the validity of. So the first example here is as following. If you are pregnant or over 65, then you cannot use the hot tub. You're not over 65, you can use the hot tub, therefore you're not pregnant. So notice that here I've omitted putting the horizontal line. Now, basically, as long as you have either horizontal line or your therefore symbol, you are pretty safe in terms of being understood what the premises and what the conclusion are. First of all, I would like to turn this into the symbolic form so that I can either use rules of inference that are obviously written in symbolic form to abstract them from any particular actual use case, or have a truth table where my propositions will have either true or false as their truth values. Now, I can write out what each proposition means, but I'm going to be a little bit lazy and simply label them on the actual statements. So let's say that pregnant will correspond to proposition P, being pregnant, you're either pregnant or not, it's clearly a proposition. Being over 65, I'm going to denote by R, and then the ability to use the hot tub will be represented by H. Okay, so now let's try to write down the whole argument in the symbolic form. First of all, I have if you're pregnant or over 65, so P or R, then you cannot use the hot tub. Implies no hot tub for you. Then I am told you are not over 65. Being over 65 was denoted by R, which means that this corresponds to not R. And then finally, my last premise here is the fact that you can use the hot tub, which corresponds to H, so I have H as a premise here. And the conclusion that that is drawn by this argument here is that you're not pregnant. Being pregnant is P, so being not pregnant is not P. Now, there are 2 ways of going about proving the validity or invalidity of this argument, and that is using rules of inference or using the truth table. I'm going to go with the rules of inference in this case, but again, if you feel like you would like to do a truth table instead, the method is not specified, so you can choose whatever you would like to do. Now, just to give myself a little bit of room to work here, let me move this around. So, in writing out the actual steps, I'm going to rewrite my entire argument and then label these things as 1, 2, and 3. And again, for each of these steps, I'm going to justify why I can include them so far. So these guys are all premises. What can I conclude from these so far? So again, thinking about what are the forms of the rules of inference and what structure am I seeing, I would like to eventually conclude not P. So I certainly would like to involve a statement that has a P in it. So what do I have here? I have a conditional. Something implies something else. And then I have that something else here in the negative, right? These two are the opposite. So I can spot, again, this is going to come with practice. It's not like this is the first example I'm doing, and therefore everything should be that easy to spot. Spotting things really is actually hard work. But I can spot that this, together with the opposite of the conclusion, is going to be modus tonens as my argument form. Right? So here's what I have here. I have the conditional, and the next premise is the opposite of my conclusion in my original conditional, and the overall conclusion I can draw is the negation of the premise. So again, this is essentially a contrapositive, which is why if I applied modus tollens in this example directly, I would have actually been able to skip one step. So applying the two of them together, I can see that modus ponens will give me the negation of the original premise. So not P or R. Again, I have to include justification. This is from 1, 3, and modus tollens. Now, this isn't particularly useful because the negation is on the entire statement, and I would like to see pieces of it separately. So we can apply a rule that we have, again, proven not in this section, but before, be logically equivalent to putting the negation into the brackets. Remember the De Morgan's laws? I'm going to negate everything in the brackets and flip the actual operation. So this comes from 4 and De Morgan's law. Okay, once I have that, it looks like I'm in good hands. Again, thinking of keeping my eye on the prize here, thinking of the fact that I would like to draw not P as a conclusion, I wonder if I can already do that. Because what I have is not P and not R. So I have two things connected with an and, one of which is the conclusion that I would like to actually get at. Let's take a look at the rules of inference here and remind ourselves of the specialization. I start with the two propositions connected with an and my conclusion is either one of them. So P, I can also have the exact same specialization with Q. If I have P and Q, then each one of them separately must also be true. So here, my next line is the fact that if these two are connected with an and, then I can conclude either one of them, not P. So this is from 5 and specialization. And that is, of course, the actual conclusion that was drawn here, which means that this argument is valid. Excellent. Let's take a look at what we have coming up. So this example has 3 arguments, and we are actually only given the premises. Notice that there is no horizontal line and then there is no therefore. So we don't actually have a conclusion. Here, we're asked to give a simple conclusion to each argument, assuming all of the premises are true. So these are our premises. We're going to try to figure out what we can conclude from them. So what do we have in this case here? I have P implies not Q, not R implies Q, and then P. What is my potential conclusion here? Are there any rules that I can apply to my premises? Well, again, just to keep track of what I am doing, I'm going to write out all of the premises on the side here and number them so I can refer to each one. So I can spot that I have P implies not Q, and then I have P. Well, that is a direct application of modus ponens. So my conclusion here can actually just be not Q based on 1, 3, and modus ponens. Right? I have the direct implication and then its own premise resulting in the actual conclusion of the original premise. Can I apply anything else maybe? Because this is a pretty simple conclusion, but is that the only one? There could be more conclusions than one, right? I can also spot, for example, that I have not R implies Q, and then my newly concluded not Q. So I am denying the conclusion here, which by modus tollens will tell me that the negation of the original premise is also true. So my conclusion here, applying these two to each other, will be negation of the not R, which will be R. So that is by 2, 4, and modus tollens. And these are my two potential conclusions. Maybe you can play around with them a little bit more and conclude something different still, but I'm going to stick to these. So my conclusions here can be not Q, Or maybe I could have concluded instead, if I kept going, that I have an R here, right? Either one of these will technically be correct. They're simple and they're certainly correct conclusions. Let's see what we can do with the next one. So we're back in the case of starting out with the word forms, and therefore, before we can do anything, we have to turn them into symbolic form. The program is running if and only if the computer is working. Again, I'm going to be a little bit lazy and label the actual propositions within the argument, whereas really my advice to you is to write out what each proposition means. So I'm going to say that the program is running is going to correspond to the proposition R. I normally try to label them using some kind of letter in the wording, so my brain kind of comprehends that a little bit better. If and only if the computer is working. Working will correspond to W. Again, the proper way to do it is to really say R is the program is running, and so on. I'm going to skip the steps so you don't watch me write all of this out, but I encourage you to. I know, such a hypocrite. Next line, the computer is working or the power is off. This is a proposition I haven't seen before, so let me label that too. The power being off will correspond to, let's say, F. The power is on. Now, do I really need a new proposition for this, or can I use something that I already have? The power is either on or off. We're not talking quantum physics here. So the power being on corresponds to not being off, which means that this is going to be not F. And once I have that, I can write out the actual form of my argument. So let's go through it carefully. The program is running if and only if, remember the biconditional, if and only if the computer is working. The computer is working or the power is off. The power is not off. And that is what I have so far. Okay, so maybe I'm going to label these right here as my premises. And I'm going to see what kinds of conclusions I can draw from these. So again, thinking of the rules of inference, what are the potential rules I can apply here? Maybe let me move all of this over to the side where I have just a little bit more room. Looking at these two together, W or F, and then not F. So I have a disjunction and then a denial, a negation of one of them. If we flip back to our rules of inference here, I will notice that this is exactly the elimination. I have an or and then a negation of one of the propositions, which means that I must conclude that the other proposition must be true. So my conclusion here is if I put two of these together, if F is not true in this disjunction, then W must be true. So my conclusion here is W, and that comes from 2, 3, and the elimination. So my simple conclusion can just be W, which corresponded to the computer working. So here I can say, therefore, the computer is working. But just like above, I'm wondering if I can draw any other conclusions. Well, the one premise that I haven't used yet is this first one. The program is running if and only if the computer is working. Now remember that the biconditional means that it's a logical equality of the sorts. So they will have the exact same truth values. So this is essentially a logical equality. So if my computer is working, so I was able to conclude W, that means that I should be able to also conclude R. Now, in our table of inference, I don't have a rule that corresponds to it. So I wonder if I can somehow, first of all, break up this biconditional and then hope to apply one of the rules of inference. And that is in case true. Remember that the biconditional, we've proven, is equivalent to the two directional conditionals. R if and only if W means R implies W and W implies R. And all of my statements here are connected by the and to begin with, so I can list these two separately. So this comes from the one and the definition of biconditional. Now, is there anything I can use to draw R as a conclusion? Well, that's pretty clear. Whoops, can be here. There we go. 4 and 5. So I have W implies R and then W, which by modus ponens will give me R. So my last line here will be R, and that is from 4, 6, and modus ponens. So my alternative conclusion to this is the fact that the program is in fact running. Now, there could be other conclusions still. It seems that I've been able to draw the conclusion based on both the variables R and W, and I already know that the power is off, so there's nothing that I can conclude about F that hasn't already been said. So it seems that I've exhausted my conclusion possibilities here, but in other cases, you can look further and see if you can simplify more. In the last example here, if today is Friday, then we will drink Prosecco. If people are not coming over for dinner, we will not drink Prosecco. People aren't coming over for dinner. Sad day for us. Once again, let's label things. Today's Friday will correspond to F. It's capital in Friday. I'm going to keep it as a capital F. We will drink Prosecco will correspond to the capital P. If people are not coming over for dinner, we will not drink Prosecco. So I don't have to relabel this. This is already just not P. But then I have to label not coming over for dinner. Now it's completely up to you. Notice that it's not coming over for dinner here and people are not coming over for dinner here as well. So you could label not coming over for dinner as just D. Alternatively, you can label coming over for dinner as D and then have to include not as the additional operation. I'm going to do it directly and say that people not coming over for dinner corresponds to the variable D. So then what do I have altogether? If today's Friday, then we will drink Prosecco. If people are not coming over for dinner, which again, in my definition is D, but in yours might very well be not D, then we will not drink Prosecco. People are not coming over for dinner. So what are my potential conclusions here? Again, let me just shift it over so I have a little bit of workspace. By now, you should already be used to spotting simple forms of modus ponens and modus tollens, so I can see that between the two of these, by modus ponens, I can conclude not P, right? Something implies something else, and I have my original premise, which means that I get back my original conclusion. So I can conclude not P here. Apologies, I forgot to mention that these are my premises, and this is concluded by 2, 3, and modus ponens. So one of my conclusions is not P. So we will not drink the Prosecco. So therefore, we won't drink Prosecco. Is there anything else that I can conclude? Well, let's see. I've concluded not P here. Can I use that with the only other premise that I haven't yet managed to employ? I have F implies P and not P, which is the negation of my original conclusion here. So by modus tollens, I can conclude not F. So in my next line here, I can have not F, which comes from 1, 4, and modus tollens. Now, not F corresponds to it not being Friday, so that is my alternative conclusion. Today is not Friday. Indeed, today is Wednesday for me, so we are even factually correct in this case, okay? Again, maybe you can keep going and draw conclusions on something else, but it looks like I basically exhausted my possibilities here. I already know people are not coming over for dinner, so the only conclusions that I can draw are something about being Friday and something about drinking Prosecco, which are both of the cases that I've already covered here. Okay? Now, as I already said, this will take quite a bit of practice, being able to spot structures that you can draw upon from the rules of inference, and then also actually applying those rules of inference to those structures is something that will take a very non-trivial amount of practice. So pick up a book, look at the exercise at the end of the sections, and try to do as many of them as you can until you feel comfortable with it. Another thing that I will point out once again is in word problems, you are free to assign your variables as you see fit, and you should write them out so that it's obvious what your assignments are. In the case of constructing truth tables, also be sure to then highlight all of your critical rows, and if you produce a counterexample, actually state it out so that this can be supporting evidence for why you think that the argument is invalid.